This is Dr. Holt, Subatomic Physics. This lesson is on isotopes and mass effects. The purpose of this lesson, or this video, is to present isotopes and their definitions, and then show you how to calculate mass effect and the binding energy behind this mass effect. Isotopes. When you have two or more forms of the same element, but these forms have different neutrons than they do protons, then you have an isotope. Except for hydrogen, every atomic nucleus in normal matter is made up of protons and neutrons. The only question is how many of each there are. Typically, the number of protons and neutrons is the same. However, if we look at carbon-12, we have 6 protons and 6 neutrons. If we look at carbon-13, 6 protons and 7 neutrons. Carbon-14, we have 6 protons and 8 neutrons. In an isotope, the balance is frequently broken. For example, in uranium-238, which is the most common state of uranium, it has 3 more neutrons than does the 235 uranium, the form that is actually used in nuclear weapons. A lack of the necessary neutrons makes a nucleus unstable. Protons in a nucleus are positively charged, meaning that they repel each other. The presence of neutrons is necessary to separate these protons slightly, making the configuration stable. When the configuration is unstable, nuclear decay will occur. Light elements tend to have about as many neutrons as protons. However, when we look at heavy elements, they need more neutrons and protons in order to stick together. All the elements have a radioactive isotope, and most of them, up to Z being the number of protons, or the atomic number, up to 83, have at least one stable isotope. When you reach Z equals 84, all forms of these isotopes are unstable. Overall, 90 naturally occurring elements, there are 300 stable isotopes and over 2,500 radioactive isotopes. Isotopes can occur naturally, or they can be created in a laboratory. If you do not have enough neutrons around, the repulsive electrostatic force wins out because every proton feels repulsion from every other proton, but it only feels attraction from its nearest neighbor. On the other hand, if you have too many neutrons, the distance between the protons increase and the nuclear force becomes weaker. Since Coulomb's law of repulsion of protons inside the nucleus becomes larger than the nuclear force, the isotope will decay. Mass effect. Mass effect is the mass loss found in all compound nuclei when compared to the sum of the masses of each individual components, meaning the protons, neutrons, and electrons. The mass of a stable nucleus is always less than the sum of the protons and neutrons, and we usually exclude the electrons in the calculation of mass effect, just because they are so much smaller than what the protons are. An example here, if we look at uranium-238, it has an atomic number of 92, meaning it has 92 protons. It has an atomic mass of 238. If we take 238 minus 92, we will get 146. This defines the number of neutrons. In the table below, if we look at the protons, I went ahead and put 92 in, and the neutrons being 146. Now the mass of every proton has a mass of approximately 1.007276. If I multiply 92 times 1.00726, I will get a mass effect of 92.669392 atomic mass units. If I do the same thing with neutrons, since I have 146, I multiply it by their mass. Now their mass is slightly more than the mass of protons. When we do that calculation, we will get 147.26509 AMU. All you have to do is add up this mass of each of these masses, and you get a total mass of 239.934482 atomic mass units. Again, this is the total mass of the protons and neutrons by themselves. If we compare that to the atomic mass of uranium-238, it is a mass of 238.0289. This is slightly less than the mass of the protons and neutrons combined. The difference of that is called the mass effect. So here I went ahead and did the calculation. I found the mass defect was 1.90558. Excuse me, 1.905582. AMU, or atomic mass units. Binding energy. Since the mass of the isotope is less than the combined mass of the protons and neutrons, energy must exist, and this energy is called binding energy. From Einstein's famous equation, E equals mc squared, then we understand where this energy is coming from. One atomic mass unit corresponds to 931.49 million electron volts. This is the average of energy needed to remove a nucleon from the nucleus. Binding energy. If we divide the binding energy of a nucleus by the number of protons and neutrons, we get the binding energy per nucleon. This is a common term used to describe the nuclear reaction because atomic numbers vary, and the total binding energy would be relative term depending upon that. So from our previous problem, since we had 1.905582 AMU, if I multiply that by 931, I get the binding energy, which in this case would be 1775.03 million electron volts. Let's look at another example here. We'll determine the binding energy of helium-4 with atomic number of 2. If we look down here, it has a mass of 4.00260. Now this makes up almost all the helium in existence, which is 99.998%. So here, since I can calculate the number of protons because I have the atomic number, so it has to have it has to have 2 protons. If I take the 4 minus the 2, then I know I have 2 neutrons. If I multiply each of these times each atomic mass, we will get these values here. At this point, I just sum up the total mass, and I get a mass of 4.03182 AMU. However, helium-4 has a mass of 4.00260. If I take the difference of that, then I get a mass defect of 0.029282 AMU. If I multiply that by the binding energy coefficient, then I can calculate how many million electron volts I have. In this case, it would be 27.27589 million electron volts. Again, I hope this video helped you understand what an isotope is, and I hope you understand how to do the calculation and calculate a mass defect, and how to use that mass defect and find what the total binding energy is.